Welcome participants to the 45 the session of day 6 of Wadla 3.0 on topic recent trends in deep learning and application. Today we have with us Dr. Abhishek Ghose from 24 by 7 AI USA. He is going to talk about controlled text generation in LLMs. Before starting his talk, so I would like to introduce Dr. Abhishek Ghose. So Abhishek Ghose is director in the data science group of 24 by 7 AI at their headquarters in San Jose, California. His team works on various applications of AI ML, especially related to LLMs, NLU, XAI embeddings, multi-armed bandits, and optimization. He holds a PhD from IIT Madras from the Department of Computer Science, where his work explored interpretability of machine learning models. He has been working in the field of AI ML since 2007 and possesses more than a decade of experience in deploying real-world AI ML solutions. So, welcome, Dr. Abhishek. Now the session is over to you.
Okay, thank you. Is everybody able to see my screen, the slides, the cover slide really?
Sir, have you shared your slide, sir?
Uh, are you not able to see it on the screen yet?
Yeah, no, sir.
Oh, okay. Let me try again. How about now? Are you able to see it now?
Yes.
Okay. So let me go to full screen mode. You're still able to see the slide, the cover slide in the full screen mode?
Yes.
Okay, so let's get started. So the topic I had picked for LLMs, and thanks, Dr. Rakesh, for inviting me. So the topic I had picked for today's talk is something called controlling text using auxiliary models. I think the name changes quite a bit because it's a slightly underexplored area, but it is actually a very interesting area for energy models. And the way I would hope the talk goes is that please stop me whenever you have a question. Ask me right there. I think that provides richer context for everyone, just not you. So please stop me. Please interrupt me and ask questions. Okay. So this is the team that has worked on this specific project. So I have Joshua from Australia. Sashank used to work with us. He has recently joined another company, and that's me. And this is the team that was devoted to controlled energy. We have a larger group, but this is the subgroup that worked on this problem. So let's get into the topic. Right. So when I say control text generation, you might be wondering that, well, I mean, there are ways to control what LLM produces in various ways, right? I mean, prompting being the most popular one, and then if you have fine tuning, right? Then why do we need another way to control outputs, right? So I have listed some pros and cons of each of these approaches. So, right. So prompting is definitely the easiest to get started with, right? Especially since you can write instructions in plain English, right? The problem with prompting is that the results can be imprecise, right? Sometimes if you want very precise outputs, or if you want the outputs to have very precise properties, you have to struggle with creating the right prompt to get that, which can be difficult. And one problem with prompting, which happens in the industry, which happens with us a lot, is that um, how easy it is to get to a perfect prompt depends upon the model quite a bit, right? With chat gpt you might be able to get to the right prompt very easily, but with smaller models it might be a bit of a struggle. That's one. And the second one is, today if you are using chat gpt and tomorrow for some reason you decide that you'll use Gemini from Google, there is no way to transfer the optimal prompt from chat gpt to Gemini, right? You might have to do the exercise of prompt tuning again for a different model, right? So transferability is not simple, right? So this is a problem that we have to struggle with a bit. Then the second way to adapt LLMs to your task is fine tuning, right? So this is great, this works fairly well, right? But there are still some sort of downsides. right? So because you are rewriting model weights or you're learning new model weights, as is the case in LoRa, this can be a bit expensive, right? The second problem is for enforcing semantic constraints, right? So if you want to say that all output should sound very polite, or and just as a thought exercise, all English output should follow Shakespearean English, right? For those kind of very specific requirements, it might be hard to get fine tuning to work for you, and that's partly because the problem might be under specified because of the data set, right? So if you provide a data set, let's say you want to adapt the prompt, so the model to your domain, and you also want the model to adopt a particular tone when it is responding. How do you tell the model which parts of the data set to adapt, right? Does it adapt the substance or does it adapt the style, right? It's hard to sort of be very specific in terms of what the model should be picking up from your data set, right? So it's a ill-defined problem, so fine tuning cannot solve that, right? And it might also be possible, this is the third point, 2.3, it might also be possible that you have a data set that adapts the LLM to the problems in your domain, but on top of that you might want to say that, okay, adopt the persona of a be very formal in your responses or be very informal in your responses, right? So this is like the CSS to your website, right? And the content has been adapted to, but you want to impose style on top of what the fine tuning has produced, right? So that becomes a different challenge, right? So the third one, number three here, is what we are going to talk about, is how do we so the third way to sort of control the generated text is you can control it at the post processing stage. So for example, um, when at the output layer the model has a distribution, probability distribution over the various symbols over the vocabulary, you can fiddle around with the probability values over each of the symbols, right? So in a way you're sort of hacking the model, fooling the model in believing that the probability weights are different than what it has produced, and making it therefore produce a response that you want, right? So it gives you fairly fine grained control. Not everything is bright and rosy. We'll talk about some shortcomings with this approach as well, right? So this is a relatively underexplored area, I think, right? Because most of the developments you see in this area come from either prompting or fine tuning. But as we'll see, we'll cover a couple of techniques here. This is actually quite useful, right? And and my personal view, like having seen various models in the industry, having tried to tune some of the self-hostable models for our use cases, is that to get the results you want, you may not have the luxury of just saying that, oh, I'll just use prompting for my use case, I don't need the other two. Sometimes you might need a combination of techniques to get the results you want, right? So sometimes picking one over the other might not be an option, you might have to do all three. Okay, so let's move on. So okay, so what do I mean by post processing, right? So you have so like I said, and I'll show a schematic in the next slide. So the idea is that you don't touch the model, you do something after the model has already decoded or is about to decode the output, right? So you don't touch the initial parts, you just hack the end part, right? And so there are like broadly two sets of techniques that fall in this. So you can change the decoding algorithm, which again we are not going to be we won't cover. But the second one is the interesting bit, which is the model has produced a output distribution, now you change it, right? And the characteristics of this latter category are you are editing the output distribution. You typically need an auxiliary model. So you have the main large language model, which I'll be referring to as the base language model, base LM. You'll see that on the next few slides, right? So you use an auxiliary model in addition to the base LM to make these edits to the distribution. Um, the positive thing is you don't have to touch the base model. It does not require training or fine tuning. And the fourth point here is again a positive point, is that the constraints that you want to impose on the generated text can be fairly general. right? It's not like you have to express the what you want as a rule, or express it as a finite automata of some sort. You can actually learn a model that can take a text and just give you a value saying that this follows your constraint or this does not follow your constraint. It can be that generic, right? And so I talked about a constraint model in number 4, and there is an auxiliary model that I talked about which edits the distribution, right? Sometimes they can be the same. We'll see one technique where they are the same model, and we'll see another technique where they are different models, right? The real uh, the real appeal of this technique is that it's non-invasive, so it's operationally very attractive, which means that I can treat the LLM as a black box, and I can treat the constraint model as a black box. I don't have to change either of them, right? But I can still sort of adapt what the LLM produces to what I need, right? Not only do I not have to touch them, I also don't need to be aware of that internals, right? And if you see the footnote here, this is especially relevant in the industry where you might be using models of Amazon SageMaker or some Azure service, so you don't even know what the internals are. You are just using the model as a service endpoint, right? So this makes it operationally very attractive that I don't have to really know how the models operate under the hood, but I can still adapt my LLM to something I want, right? And my the goal of this talk is to give a flavor of this area. Like I said, it's a little underexplored, so I think I'm doing my part in making this a little more well known. And we'll cover two techniques, fudge and nado, in the next few slides. So before I move on, are there any questions? No? Okay. So I said that you are imposing some constraints on the text, generated text. So now the question is, like, what exactly are we looking for? What would be some examples of the outcome we are shooting for, right? And this is an example from the fudge paper, right? So these are all output responses from a base language model, and the input prompt to all of these examples was the phrase "more importantly," right? You'll see "more importantly" is the prefix for all of these output responses. And I had like the fudge, the example sort of was executed by giving context military or legal or science to the base model, right? That was the constraint. That was a topic constraint. So the base LM was asked to produce something related to the military topic or the legal topic or the science topic with the input prompt "more importantly," right? And you can see that the completions, whatever comes after "more importantly," are topically very different and tied to whatever constraint was provided quite well, right? So this is around science, this is around legalities, and this is around military, right? And why is this of interest to us is that, so if you don't know, we are in the business of customer chatbots. That's one of our primary businesses, right? And when you make a customer chatbot, you might want it to follow certain policies or certain topics, and this is why we are interested in this problem, right? So for example, if you have a bot for a particular hotel chain, they might have a certain policy that if somebody wants to change their booking, the policy is that you have to ask for authentication information first, right? And maybe your chatbot might be doing it like 70% of the time, but a policy is a policy, so that's not good enough, right? So you need this kind of constraints imposed upon the output to say that 100% of the time you need to follow the policy of asking for authentication information, right? So that's our interest in this problem. Okay, so I'll get into the details now. Again, if there are any questions, please stop me. um, so this schematic you see at the top of the slide is how a autoregressive LM language model works, right? Your language model may not be autoregressive, but most popular models like ChatGPT, Gemini, most transformer architecture models are autoregressive, which means that the output sequence, right? So here I am showing an example of a popular rhyme being produced: Humpty Dumpty sat on a wall, right? The output sequence is produced one symbol at a time. And the way it works is that when you have a particular input at a particular stage, over the whole vocabulary, your vocabulary may be thousands of words. Each word gets a probability value assigned to it, and based on some heuristic, you pick a word taking into account that probability value. Right. So you see this vector has a length of v. V is the vocabulary, and what is happening here is that you picked the word sat. Maybe you picked the token with the highest probability. Maybe you did some other form of sampling from this vector, maybe nuclear sampling, right? But the idea is that you have some vocabulary over which you have this distribution of probabilities, and you pick the best symbol, best token based on these probabilities, where the best is defined according to your sampling criteria, right? So you picked sat here, and autoregressive means that the word that you have picked also becomes part of the input in the next stage, right? So the input here was Humpty Dumpty, it produced sat. In the next stage, you have Humpty Dumpty sat as the input, and now it produces on, right? Now this becomes part of the input and goes to the next phase, right? So you're producing one symbol at a time till you produce a end of sentence special symbol, right? And this is how, like in a nutshell, how autoregressive LMs work. And like I said, there are some exceptions. You'll see that mentioned in the footnote, but by far most of the models you encounter today, language models you encounter today, are autoregressive, right? And writing it in the math form. Okay, so let me introduce some notation here. So the idea is that you have some input prompt X, right? And
Yeah, good morning.
sorry, is there a question?
No, sir. Please go ahead.
Oh, okay. So you have an input prompt X, right, which is this guy here, and you are producing an output sequence Y from some universe of strings, right? So maybe if it is ChatGPT, the universe of strings, it's all of the English language, right? So and your string has a length L, which is obviously not fixed, right? Based on different inputs, L can differ. And for the math here, we'll just assume that L is fixed and it differs from case to case, but there is no subscript saying that. And each symbol, so your sequence can be divided into yi, so y1 to yl, right? And your vocabulary is b, right? And this picture I showed you here can be written mathematically as this expression, which is, you can think of your language model as producing a probability over a sequence y given x, the input, right? And when I say, so there are two probabilities we are talking about, right? So when I showed this picture here, I was talking about a probability over each symbol, right? That was being used to produce the current value of yi, right? But if you aggregate y1, y2, y3, y4, and you multiply them together, you also find the probability of the whole string occurring as an output, right? So so at a very high level, mathematically, you say that the probability of a string y of length L being produced given an input x is that symbol y1 is produced given x, y2 is produced given x and y1, and y all the way till yl being produced given x, y1, y2, all the way till yl minus 1, right? So this is sort of the autoregressive formulation, right? You can think of your language model as giving this probability p, right? So this would be like a mathematically abstract way of thinking about the autoregressive nature of your language model, right? And in this language, what are we trying to do, right? What we are trying to do is that if you have a constraint c, right, that the control that we want to impose on the output text, if you have a control c, right? Uh, sorry, I'll keep switching between control and constraint, but yeah, if you have a constraint c, the idea is that you want to modify p uh, such that instead of py given x, you want to create, you want to produce py given x comma c, right? That is, in addition to the input, your output should also be conditioned on the constraint that you have fed into the model, right? So mathematically, again, at a very high level, this does not give you any details, but at a very high level, this is the problem we are solving, right? So these are sort of the two views. This is the schematic view, and this is the mathematical view. One point about the notation which shows up in this footnote is that see, your x input and y output is sometimes, I mean, you might choose to not distinguish them because your autoregressive LM is always doing the task of completion. So you can think of the prompt as also a string, part of the string that came before the LLM kicked in and started finishing up the next few symbols, right? So in some cases, I won't distinguish between y and x, and that will be clear from context. But yeah, I mean, x is also a string, and y is also a string, and y is a continuation of x, right? So we might choose to distinguish them sometimes because it helps the math, and sometimes we don't, because in some cases that's the notation that works out better. Any questions so far? Okay, so let's move to the first one. The first algorithm is future discriminators for generation. So this is a very interesting technique. The name is a little fancy, so I'll explain what future means in a while. What the word future means, but the idea is actually quite simple. So this is, let us say, the two symbols that have already been generated, do you, and this is a formality constraint. So this is an example where you want the language model to produce responses that sound very formal. Okay, so so if you look at the language model's output, which is the this top part in blue, right, and you see the vocabulary table here, you see the corresponding probabilities assigned here, right, and you see that the words want and prefer have both similar probability weights, right? So if you were just relying on the language model, you could have gotten a sentence like, do you want something or do you prefer something, with equal probability at this point, right? And this is what the probability says, this expression, that you are producing y3 given y1 and y2, right? Now you have the constraint model, and in the case of fudge, the constraint model is a classifier that can take a string and give you a probability value of confidence value of how much it satisfies your constraint, right? So you can give it an English string, and this constraint in this example will tell it it's very formal, so that's a score of 1, or it's not formal at all, that's a score of 0, or it is somewhat formal, maybe that's a score of 0.2, right? So you have this model C which encapsulates your constraint, and it gives you a score of the extent to which your constraint is satisfied, right? And that, so you're producing your token y3, and what you do is, for different y3s possible, you concatenate it with the y1 and y2 you have already produced, right? And you ask the classifier, sorry, you ask the constraint model, which can be a probabilistic classifier, that's why I said classifier. You ask your classifier that, hey, if I had added, do you, for the sentence, do you want, what's the probability, for the sentence, do you prefer, what's the formality, not probability, formality score, for the sentence, do you does, what's the formality score, right? And you'll see that does prefer get a very high score, want doesn't get a very high score, but you have to also take into account how probable they are in the first place, right? So what you simply do is you take the original probabilities, and then you take the model scores, you multiply them, right, and then you pick the highest one, right? So now you get a output, do you prefer, and you see that prefer is way ahead of want, so you could not have produced do you want, so you just produce do you prefer, right? So this is the basic idea of fudge, right? And I'll summarize this in the algorithm here. So you train a probabilistic classifier C, which gives you a score for the, which takes as an input a string and gives you a score of how much you satisfy that string satisfies the constraint, right, between 0 and 1. That score should be between 0 and 1, right? So for example, if you wanted to produce only Shakespearean style English, you could have trained the classifier C with a lot of documents of Shakespeare's plays and a lot of documents from, let us say, current news articles, right? And at every stage, the adjustment is very simple, right? So whatever we saw in the picture, I'm just going to write it down here, which is that the probability of yi given all the symbols produced so far, and this is one example. Like I said in the previous case, I am not distinguishing between x and y, right? So in this math, I'm not, right? And the adjustment is very simple. The probability of yi getting produced, having seen the symbols thus far, is that you adjust it by multiplying it with the classifier score for y1 to yi, right? So whatever symbol you are calculating the probability for also has to be concatenated, and you let the classifier give you a score for that, and you multiply that with the original probability of that particular symbol yi, right? And that then you get a adjusted score, which I'm referring to by q here, right? So this becomes a new score, and you do your sampling, like the best nuclear sampling or best sampling, max sampling, greedy sampling based on q. You don't do it based on p, right? Fairly simple setup. um, any questions? Okay, so yeah, it looks like
Uh,
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 sure,
There is
go ahead.
one
Excuse me.
question.
So you mean to say it is boiling down to a simple case, like you take the prior probability of this distribution and multiply with the conditional probability. Is
Yes.
that? Yeah. Thank you.
So that's a good view, because this is a justification we have for this. So why, you might ask, why did I take a product, right? And this is exactly what you say, right? So it's like a Bayesian factorization, right? This product that you see, the q that you see here, right? It's almost like you think of it as a posterior probability with the condition, but this is proportional to these two these two values, and you are just basically multiplying them, right? So this is the justification. It's fairly simple, but it actually works quite well. And the interesting thing is, you can swap out C. Like, you don't have to change your base language model. You can have one C for like if you want to generate Shakespearean English, there is one model for that. If you want to generate formal English, you have another model for that. If you want to generate text that is positive in its outlook, you have a positive sentiment model for that, right? So you have this very small sort of models C, and you can apply it on top of your base language model, and it sort of modifies the output, right? So it's quite convenient to use, right? And this is, by the way, where the word future comes from in the name is, that's because you have your base language model trained on some loss function, right? You don't know what constraints will be applied in the future, but nevertheless, you can still adapt the language model without retraining, even if you build a new constraint C in the future, by just doing this kind of adjustment to the probability distribution, right? So if you remember the slides, a few slides back, I said that there is a constraint model and there is an auxiliary control model. So in the case of fudge, they are the same, right? The constraint model is C, but I'm using the probability scores from the constraint model to modify the scores of the base language model. So that also sort of plays the dual role of being the auxiliary model, right? But this is not always the case. In fact, we'll see in a while that in the case of NADO, the other method, the auxiliary model and the control model are different models. Okay. So the other thing is, right? So, okay. So now the challenges. This is number 4 here. So one challenge is that, I mean, this equation looks very simple and all, but the thing that we have to be careful about is these two probabilities are actually not compatible, right? This probability comes from the classifier we have learned, the control model, and this probably comes from the base language model that we have learned, right? And the pre-trained language model maybe that we are using, maybe we are using BERT, right? So most of the experiments that we did, for example, use distal BERT. uh, so this is not compatible in the sense that during training, the distributions of various strings that these models might have seen could be very drastically different, right? So while the math looks very simple and elegant, there is a lot hiding under the hood. The two probabilities that you see are coming from different models, and therefore they might not be exactly compatible, right? And another way to sort of phrase this problem is that the correction that you are applying, right? This correction that you are applying is only dependent upon the model C, right? It does not take into account the property of the base language model, right? What if your base language model was trained in a way that it is very hard for it to satisfy the constraint C, right? Then you might want to correct its probabilities a little more aggressively than the case where it was trained in a way that it is easy for the base language model to satisfy your constraint C. In that case, you might want to just mildly change the distributions, but not much, right? So it really does not take into account how aligned the base language model is to the constraint that you're enforcing, right? It just applies this constant correction to everything, right? And that sort of goes to the heart of the issue, which is that the two probabilities are not compatible, but we treat them as if they are, right? The other problem is this is a testing this is a sorry this is a training time challenge and operational challenge. The other problem is that your C, right, has to predict at on partial strings, right? Here it is predicting on the first three symbols of the sequence Y, right? And it has to do it for the first four symbols and the first five symbols all the way up till the end of sentence symbol. What this means is that if your training data has full sentences as its input, right, let's say this is the Shakespeare's plays data set, and this is a quote from Shakespeare: nothing can come of nothing, right? you cannot actually you cannot actually train a very reliable C just on this sentence, because you are going to invoke C to classify the first two words, classify the first three words, classify the first four words, etc., right? And to therefore to make a reliable classifier C, for every sentence needs to be sort of decomposed into all the prefixes possible, right? So this one instance in your training data will have to be broken down into all of these instances here, right? And this can create a severe bloating of your training data, and might make it computationally hard to create a reliable C, right? So this is a problem that we have faced. We have a lot of customer data, and to actually create a reliable C, so that we can apply fudge, it's actually very hard, because you think that you have a data with 10,000 points. You suddenly, when you do this prefix decomposition, you end up with something like 60,000 points, right? And suddenly your estimates of how hard this problem changes. You can avoid this to some extent by learning something like a RNN, which takes the whole sentence but still can predict at every step what CI is. But then we must sort of reinterpret the fudge technique under a new light. So fudge's claim is that you can use any classifier C, but then we are saying that we cannot use any classifier C. We'll have to use something specifically like a RNN to actually deal with this problem, right? Um, so this is about fudge. This completes this part, and we will see next how Nado sort of improves over some of these challenges. Any questions? Okay, so let's go to Nado. So Nado is a little more complex than fudge, and but it actually fixes some of the issues that we saw in fudge, right? And the cost of those fixes is that the model becomes complex. And the issues that it fixes is the first one is the probability compatibility issue, right? That in fudge we don't really care about how misaligned the base model might be with respect to constraints, and Nado fixes this by creating another auxiliary model R, which is different from the constraint model C. And in fact the name Nado is for that auxiliary model R. The auxiliary model R is what's called Nado in the paper, right? And another advantage of NADO is the operational issue we talked about in the previous slide, is that your oracle in NADO has to be sequence level, which means oracle or constraint model has to be sequence level, which means that you can give it a sequence and it will tell you whether it satisfies your constraint or not, right? Given the sequence level model, it automatically creates a token level distribution, right? So you don't have to struggle at the training phase creating all those prefixes, because NADO internally has a way of dealing with prefixes, right? Whether that's good or not, that's a different question. That is not obvious from this slide, but operationally that makes your life easier, right? So these, according to me, these are the two big benefits of NADO, right? And you'll see that I have mentioned two papers here. That's because the original paper came out in 2022, and there was a follow-up work by some of the same authors called NADO++, which came out very recently, where they address some of the operational issues that that are present in NADO as well. Okay, so with NADO we'll have to get into a bit of the math, because like I said, the probability incompatibilities are a little hard to fix, but they can be fixed, and we'll see how. Right, so your oracle here is a sequence level Boolean function, and by the way, again, note the change of notation here. I am making a distinction between the input x and the output string y, because with NADO that formulation works better. So you have the sequence level Boolean function that maps to just 0 and 1, right? No, does not produce a score, it just says whether it satisfies the constraint or not. Now we want to determine the optimal sequence level function that honors the constraint C, right? And correspondingly, we want to also find the optimal token level distribution, because when we're actually running the model, what we really need is to adjust the token level probabilities. If you give me optimal sequence level correction, I can't do much with it, because autoregressive model produces one symbol at a time, and I have to fix things one symbol at a time, right? So the optimal sequence level distribution is a nice thing to have. It's a academic interest, but I really need the optimal token level distribution, right? So NADO makes these assumptions. These are all very reasonable assumptions. So they first say that the sequence level optimal distribution Q star y of x can be broken down into an autoregressive token level distribution. So this is very similar to a few slides back we looked at when you write the base LM's probability as an autoregressive term. This is what it looks like. So NADO says that, well, the base LM is autoregressive, so we'll just assume that the adjusted distribution is also autoregressive, right? And this sort of gives you a clue as to how they can take a sequence level distribution and they can break it down into token level. They basically use this assumption that Q star is autoregressive, right? Now the second point is, what does Q star look like, right? So we are just saying Q star, we don't know whether it's a Gaussian, whether it's a particular distribution. So now we begin characterizing Q star, right? So we say that one property that Q star needs to have is that given a input and a sequence output, if the output does not satisfy the constraint, that is C of x comma y 0, then Q star of y given x should also be 0, right? That's fair, because that's what we are after, right? And the third one is again like a fairly reasonable assumption, which is that we want a distribution that honors our constraint, but we don't want the distribution to veer away too much from the base model, right? Because the base model might have other things going for it, right? Maybe it is good at reasoning tasks, maybe it is good at pulling up real world facts, and just because we want the base model to be formal or respond in Shakespearean English, I don't want to give up on all those properties. I still want it to be good at reasoning, right? So we should not be changing the base model's probability too much to the point that it becomes useless in other ways and just satisfies our one constraint that we wanted, right? So the way to enforce that is, they say that the sequence level distributions P, Y, given X, which is the base model's distribution, and Q, Y of X, which is the adjusted distribution, the KL divergence should be between them should be as small as possible, right? So that we have the base model in spirit, right? The constraint is imposed, but the base model should still be there somewhere, right? We don't want to break the base model. Okay. So two more notations, and then we will jump into why Nado works, or how Nado works rather. So here we now calculate. If you remember, one of the problems with Fudge was I said we don't know whether the base model is aligned to the constraint in the first place, right? So in Nado we explicitly calculate these quantities. So there is this prefix p, r is that quantity, and there is this prefix p that says that this is being calculated for the base model, and the superscript c is for the constraint. And what we are saying is, given an input x, right, what is the expected alignment of the base model, right? And the expectation is over all the strings that you could have produced from the base model with input x, and the expected satisfaction is essentially the expectation over all the 0 1 values produced by your constraint model, right? And I did we define this quantity for just the input, but we also analogously define this quantity for the partial output, which is you have the input x and you have already produced your symbols up to I minus 1 starting from y1, right? And now you are saying that whatever is likely to be produced next, what is the expected value for constraint satisfaction, right? So it is essentially the same quantity, but you are now conditioning on the fact that you have already produced some of the symbols, right? So this in some sense calculates the alignment of your base model, something that we completely ignored in Fudge, right? And because we have characterized things in this manner, right, we will see that this third property, like where we find the optimal distribution, is actually very simple to calculate, right? So typically when we see KL divergence show up, like let's say in variational inference, we suspect that there is a heavy optimization coming next. Here surprisingly it's just a one line solution. So right, so the optimal q star for sequence is actually a one line solution, right? So let's again characterize q star a bit more, the valid distributions a bit more, right? Again, like we haven't really spoken about q star, we just said that it should give those y's a weight of 0 which do not satisfy the constraint, and we also said that the KL divergence should be very less with respect to the base model, but we haven't said much beyond that, right? So we are now saying that give me so the q distributions that I'm interested in should have this property that all the y's that you can generate given any x, right, should be 0, should have a weight of 0 if the constraint satisfied value is 0, right? Again, I'm not again saying anything very specific about q, but I'm saying that this set capital Q characterizes all the valid distributions that we are willing to consider, right? So notice that instead of saying that every single y has to be 0 where the constraint fails, I'm summing up all those values and I'm saying the sum has to be 0. But since this is a probability, um, and therefore each of the values are a small positive value or a 0, the only way the sum can be 0 is if the individual values are 0, right? So it's a mathematical shortcut to say that all strings should satisfy this probability. I'm just using a sum. Now let's look at the KL divergence term. We said that it cannot veer away too much from the base model, right? And the reference distribution in the divergence I'm using is the base model's probability, right? What's the distribution that comes closest to the base model's probability, right? So the highest value of KL divergence you could get is if Q is equal to P, correct? But obviously you don't want to give weights to things that violate the probability constraint. So what we are going to do is we'll say that P has, so there are a lot of these strings y, and P gives a probability value to each of them. It assigns a probability value to each of them. For strings that satisfy the constraint, I won't touch the probability. For strings that violate the constraint, I'm going to force it to 0, right? That's the best P you can hope for, right? Because like tail divergence wise, that's the closest new distribution you can hope for, because whatever it was producing, if it does not violate the constraint, it gets to keep that probability value, right? So once you do that, you have set a lot of these violating strings, the probability corresponding to the violating strings to 0. You obviously have a new problem, which is that the remaining probabilities don't add up to 1, right? So now you put this normalization term. You say that, okay, the best Q star I can get is that I'll use Py by x, and I'll multiply it by Cx comma y. Wherever there is a violation, the numerator disappears. Wherever there is no violation, it just gets multiplied by 1, which means it gets to keep its old value, right? But I have to put the normalization constant in the denominator, because I have set so many things to 0, they don't add up to 1, right? So I take this quantity, add it over all y, but we have seen this quantity before, right? This quantity is essentially this quantity, right? So somehow magically, it turns out that the optimal sequence level distribution we can get is actually a very simple quantity, right? At least mathematically. The real problem is we don't know what this denominator is, right? We are saying what is the innate innate alignment of the base language model with the constraint, right? There is no easy way to compute this quantity, but at least on paper it's a very simple expression, right? And this is an intuitive thing. First of all, you are taking into account a property of the base language model which we ignored in fudge, right? And it's also intuitive because if this value is small, the alignment of the base model is low, right? The P gets multiplied by a higher value, right? So you are saying that if the alignment is low, the adjustment is higher, and if the alignment is high, the adjustment is lower, and you would expect that, right? So that's kind of intuitive. And I won't be going into breaking up this Q star sequence level to token level, but this is what that looks like. Again, you don't have to go very deep into this expression, but there are some interesting things to note, a couple of them, right? So the partial alignment quantity that we had calculated now shows up, right? Okay, so the first thing to note is that this is a positive number, right? So much like fudge, the correction to P is a multiplicative factor, right? In fudge, we multiplied it by the score of C. Here, we multiplied it by the slightly complex ratio, but at a high level, you are still multiplying, and that's the adjustment, right? So not very different from fudge, but the terms themselves are kind of complex, right? And this sort of also makes sense because you're taking the ratio of alignment till symbol I minus 1 divided by the alignment till symbol I minus 2. So the idea is that if you're going in the right direction, right, in terms of alignment, right, then the numerator will be greater than the denominator, right? You are basically forcing, like you are basically pushing P in that direction. You are saying that, okay, if the numerator is greater than the denominator, that's the right direction to go, right? So somewhat like at a hand wavy level, maybe the final expression makes sense. And the way you go from the sequence level optimal distribution to the token level is because of the autoregressive property that we talked about. So if you look at the math, again, it's a few lines, but that's the property they use to go from sequences to individual tokens. Okay, so this is the sort of the optimal Q we are looking for. But like I said, these quantities are very hard to know, right? I mean, if you look at the math, we are saying that all possible strings that X could have produced on the base language model should be used to compute these quantities. We cannot do that for most large language models. The space of strings that can be produced is huge, right? So now you set yourself on the task of approximating these quantities, and this approximation model is what is known as NADO. So if you look at the expression here, this is what we want to approximate. Actually, NEI, this is what partial alignment is what we want to approximate. And when I'm talking about the approximation quantity, I'll replace the p, that is a subscript, with a theta, because that would be the approximating model's parameters, right? But the job of this guy is to basically approximate this guy. The way they do it is they take any sequence to sequence model, right? And you sample a lot of x's and you sample a bunch of y's corresponding to this x's, right? And you for the pair xy, right? You concatenate them. That's a string. For that xy sample, right? You take the value of the Boolean value of the constraint model, right? And use it as force for teacher forcing at every step in your sequence to sequence model training, right? Using the cross entropy loss as your loss, right? So the loss is essentially cross entropy of uh, the current output of the sequence to sequence model with respect to what the constraint model says about your string, right? So now you have the sequence to sequence model, which at any partial string x, given any input and any partial string, it will give you the alignment value, which hopefully is close to this theoretical value that we need, right? So that becomes the controlling model here. And the way it works is, and I apologize for this diagram, it's not very clear. This is taken from the paper. So the way you would execute this is, so you have the base language model on the top, right? It's an autoregressive model. So at every instance, it produces py of py given x, y till some symbol y2, y3, all the way till yl, right? Conditioned on that. And you also run your NADO model in parallel, where you keep producing the alignment given x and the corresponding partial y that you have created, right? So you keep calculating these values, and based on these values, you can calculate now from your model. You can calculate q based on this very simple product, right? So this is how you adjust, right? So essentially, you have to run both these models in lockstep. And at every token, you have to do this adjustment to produce this adjusted value q. And then you do your max sampling, take the symbol with the maximum probability or something like that to produce the final output. Right. So this is how NADO sort of fixes some of the issues with fudge. So yeah, so again, like the problem of prefix training that we saw in fudge disappears because the constraint model can operate at the sequence level, right? You don't have to think that, what does the constant model say about partial strings, which was a worry in fudge. Here, note that we never actually had to use the constraint model on a partial string, right? And the control model is a separate model, and that has the ugly task of figuring out what the optimal token level distribution is, right? So that entire problem of decomposing every string into all possible prefixes so that your constraint model can deal with it kind of disappears in NADO, right? So this is NADO, and I would like to go over some of the key takeaways. But before we do that, are there any questions? Okay, so the key takeaways. So we're at the conclusion now. So the first takeaway obviously is that we looked at a different way of controlling the output of LLM, right? It's an interesting way, not very popular, but it works. And in some cases, like I said, if you want to treat your LLM and your consent as black boxes, maybe because they're both services, you're using OpenAI service and you are using Azure or something, right? Maybe this is the only thing you can do, right? Sometimes this is the only way out. Right, and we looked at two such techniques, fudge and NADO. They both operate in this autoregressive setting by editing the distribution. They're operationally attractive because they're non-invasive. We don't even need to know the internals of the two models involved, as long as the base LM is autoregressive, and the constraint model in case of fudge gives you probabilistic labels. In the case of Nado, it's a Boolean function. The difference between the big difference in my mind between the two is Nado takes into account the base model's innate alignment to the constraint that you are working with. So in some cases it will adjust the probabilities more, some cases it will adjust the probabilities less, but it's dependent upon the base model's original capability to honor your constraint C, right? This is also reflected in the fact that fudge has the same constraint and control model. The same model works as both, but Nado has a specialized control model, the seek-to-seek network that we talked about. These are reference to papers. Of course, like the presentation is a brief overview, but if you want to really look at it, the fudge paper, the archive version has a lot more details than the peer-reviewed version, and that's probably the paper to look at. And the Nado paper is very nice in the sense that it has all this empirical stuff that we talked about, but it also gives you error bounds on the approximation of R, the alignment that we saw, right? So pretty detailed. And then there is a Nado plus paper that I mentioned that goes into fixing some of the problems with the original Nado paper. So our observation has been that fudge is good for style, right? So if you want to say that only reply formally or only reply politely, fudge is good for that, or it's good for broad topic infusion, right? You want to tell fudge that talk about the weather, right? Fudge is good at that. But where we are seeing fudge failing is that when you give it very concrete instructions, like if a person comes with a account issue, you want to tell fudge that okay, first ask for the person's login, and then ask for the error that the person has seen, and then ask when was the last time they attempted to log in, right? These are very concrete instructions you might need to use in a good customer service session. This is where fudge sort of loses the plot, right? We just started looking at Nado. We are hoping that is better, but this is what we have observed. So that's it from me. Please let me know if you have any questions.
So thank you very much, Abhishek sir, for your wonderful session. So participants, I think there is one question in the chat box, sir. Could you see?
Okay. Let's see. The fudge essentially takes the dot product, but Nado, yes. Okay, the geometric way, no, I don't have a good geometric way. The paper itself just restricts itself to the math. So sorry about that.
So any other questions? Yeah, one participant.
Thank you for the lucid presentation. I'm curious to know the experiment details, but I think I can look in the paper. So it can be applicable for anything where you can have an API call and you can play with the output. Am I right?
Yes, in fact, that is why we started looking at it, because you don't have to know the internals of the models, like, and that's unfortunately a reality in a lot of industrial settings.
Yeah. Thank you for the clarification.
Yeah, and also, like, to your point, right? Sometimes what happens is that, like, if you have a constraint model, if you want to use a constraint model, maybe the constraint model comes from some other exercise that you would have done like 2 years ago, right? So for example, if you want to impose, let us say, formality, you want all responses to be formal, you don't want to, you might have already created a formality model like 2 years ago, and it would be nice if you could reuse that model off the shelf instead of retraining one specifically for your data set, right? So this is another thing that makes it very appealing, because I can reuse constraint models, which are essentially classifiers, right, that I have trained previously.
So any other questions, online participants? So I think no more question, Abhishek sir. So once again, thank you very much for joining this Wadla 3 session, and thank you very much, sir. So I think we can close this session.
Okay. Thank you.